Welcome to section 5.3, Trigonometric Equations, day 3. Today we're going to continue to solve trig equations, but we're going to use some factoring methods to be able to solve these. So the first thing is just taking some trig equations and expressions and being able to factor them. So we got 2 sine squared theta plus sine theta. So these are just expressions. We're not solving anything just yet. We're just going to work on factoring. So you can think of this as 2x squared plus x. How would you factor that problem? Well, it's a GCF. And so you would factor out the x, and that would leave you with 2x plus 1. It's the same idea. All we're doing is saying that x is equal to sine of theta and then rewriting the problem. You don't have to do it this way, but it gives you a better visual for what you have typically been doing with quadratics. So what does this factor to? Well, you would factor out the sine of theta, and you'd be left with 2 sine of theta plus 1. On B, cosine squared theta minus 2 cosine squared theta minus 2 cosine theta plus 1. Once again, if you want to replace cosine of theta with x, it would read x squared minus 2x plus 1. And then you could factor that into x minus 1 times x minus 1. Or, since x is equal to cosine theta, that would be cosine of theta minus 1 times cosine of theta minus 1. Or cosine of theta minus 1 quantity squared. Third one, 2 sine squared theta minus sine theta minus 1. So this one I won't replace and just factor it. Well, 2 times sine theta times sine theta. And then what are factors of negative 1? With your factor of 2 in front there, well, you only got factors of 1 is 1 and 1, so we know it has to be 1 and 1. Where's the negative going to go? It'll go on this side because that would give you a negative 2 sine theta plus sine theta. And so once again, if you're doing it that way, you don't have to plug in the x and everything else, but you have to have that good visual to kind of just see that. So that's what we're going to use today to be able to solve some more trig equations. So let's take a look at the first example. We're going to get 2 cosine squared theta minus cosine of theta. The equation is quadratic in form, so we do want to set it equal to 0 and solve by factoring. So we are going to subtract the cosine of theta to the other side, and then we are going to factor. Once again, if you want to replace cosine of theta with x, then factor, then plug it back in. So it would look like this: 2x squared minus x is equal to 0. Factor, in this case GCF, you'd be left with 2x minus 1, and then you set your factor is equal to 0. X is equal to 0, 2x minus 1 is equal to 0, or x is equal to 1/2. Now, those aren't our solutions because we're not solving, for x. We're solving for theta. So we're going to replace the x's back with what we originally had, which is cosine of theta is equal to 0, and cosine of theta is equal to 1/2. And then now you just got to think about your unit circle. Where is cosine equal to 0? Where is the x value equal to 0? That would occur here at pi over 2, and then here at 3 pi over 2. So for the first part of the equation, we have solutions pi over 2 and 3 pi over 2. With cosine of theta equaling 1/2, the x value would be 1/2, y value would be square root of 3 over 2, and that would be a 60-degree angle, or pi over 3. And we're only answering between 0 and 2 pi, so we only want those values. So theta would be your pi over 3's. It is positive, so cosine is positive in quadrants 1 and 4. So that would be pi over 3 and 5 pi over 3. So those are your 4 answers, and we will put them in numerical order. So that would be pi over 3, pi over 2, 3 pi over 2, and 5 pi over 3. So those would be all 4 answers to the original equation. And so as I said, if you want to use this idea of x equals cosine theta, that helps you out, definitely do it. If you feel like you don't need to, that's fine as well. Let's take a look at another problem. Example 3, we have 3 sine theta plus 3 is equal to 2 cosine squared of theta. Now this one contains sine and cosine. So this one contains sine and cosine. We need to use trig identities to convert one trig function to another. Well, we know that cosine squared can be rewritten as 1 minus sine squared using Pythagorean identities. So let's do that because now they're both in terms of sine. So that'll give us 3 sine of theta plus 3 is equal to 2 times the quantity 1 minus sine squared of theta. Let's go ahead and simplify this equation and set it equal to 0. So we'll distribute the 2. I'm going to add 2 sine squared of theta to both sides. There is no like terms because it's the only one being squared. I'm also going to subtract 2 from both sides to set it equal to 0. So that'll give me 2 sine squared theta plus 3 sine theta, and then plus 3 minus 2 would be plus 1. So that's what we're looking to factor. Once again, if you want to replace sine theta with x, it would be 2x squared plus 3x plus 1 is equal to 0. And I just use the guess and check method. It has to be 2x times x, and there's only one way to multiply to get 1, which is 1 and 1. Everything's positive, so the guess and check method only requires one guess. It's the only possibility. So it must work, and it does. So I still did check to make sure it did work in case I made a mistake. Set your factors equal to 0. So we get x is equal to negative 1/2 and x is equal to negative 1. So now I'm going to replace x with sine of theta. So it'll be sine of theta that's actually equal to negative 1/2, and sine of theta that is equal to negative 1. So where is sine of theta equal to negative 1/2? Well, the ordered pair would be square root of 3 over 2, 1/2, and that would be your 30 or pi over 6. So sine is negative in quadrants 3 and 4. So that means we would have angle 7 pi over 6 and 11 pi over 6. And then where is sine equal to negative 1? That's going to be one of our quadrantals. That's your y value. So that would be at 3 pi over 2. So our other angle is 3 pi over 2. So we have 3 solutions. Once again, please put them in order. This would be 7 pi over 6, 3 pi over 2, and 11 pi over 6. And those would be your 3 solutions to this equation. All right, on the next example here, we have 2 factors that are set equal to 0. We don't need to multiply them through. We have it set up the way we want. We can just go ahead and set each factor equal to 0 and solve. Once again, remember, we are only solving between 0 and 2 pi. So we have cosine of theta minus 1 is equal to 0. And tangent of theta plus the square root of 3 is equal to 0. Do not multiply those together because we already have it set up in factored form equal to 0. So we now have cosine of theta is equal to 1, and tangent of theta is equal to negative square root of 3. So where is cosine of theta equal to 1? Well, when x is 1, we're over here at 1, 0. So that would be theta is equal to 0. 0 is included, but 2 pi is not. So theta can be 0, but it cannot be 2 pi because it doesn't have that equal sign. It's not it's restricted to just the 0 value. We don't want any repeats. So theta is only equal to 0 on that one. And then what angle gives you the negative square root of 3? And that would be the ordered pair 1/2 square root of 3 over 2. So if you take y divided by x or sine divided by cosine, the 2's cancel and it's just the square root of 3. So this would be our 60-degree or pi over 3 angle. So we want negatives. Tangent is negative in quadrant 2. So that's 2 pi over 3, and quadrant 4, which is 4 pi over 3. So once again, we have 3 solutions on this one. Theta would be equal to 0, 2 pi over 3, and 4 pi over 3. And once again, these are only the angles between 0 and 2 pi, not including 2 pi. We'll include 0, but we will not include 2 pi. And so those are the 3 solutions. You can always plug those back in and check to see that they work if you want to. And the last example I'm going to look at in terms of the solving trig equations using some identities that we know, We have cosine of 2 theta plus 6 sine squared of theta equals 4. Well, cosine of 2 theta had 3 different equations we could use, but we want it in the form of the same trig function. We don't want to just convert it to anything, so we want to pick the one that already has the sine squared value, which would be the one in the middle here. So we're going to replace cosine of 2 theta with 1 minus 2 sine squared theta. 1 minus 2 sine squared of theta. So 1 minus 2 sine squared of theta, so that's what replaced the cosine of 2 theta, plus 6 sine squared of theta is equal to 4. Now I didn't need to put that first one in parentheses, so we can just we can combine our like terms here. That would leave us with 1 plus 4 sine squared of theta. And if you notice, once again, we could replace x with sine of theta, but if we're paying attention here, we have sine squared as by itself. We don't have another sine value. So this would be sine squared right there. So we're going to isolate the sine squared. So we'll subtract the 1. That'll leave us with 4 sine squared of theta equals 3. Divide by 4, and that will give us sine squared of theta is 3/4. We need sine, so we'll take the square root of both sides. Don't forget the plus or minus. So that would be sine of theta is equal to plus or minus the square root of 3 over the square root of 4, which simplifies to 2. Now we can answer the question. What angle gives us a y value of square root of 3 over 2? That would be pi over 3. And since it's plus or minus, we want every angle from quadrant 1 to quadrant 4. So we will list all 4 of them. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And those will be the 4 solutions for that equation. And so now you have your summary. Think about all the different types of equations that we solved using Pythagorean identity, also using double angles. Also, which ones do you factor using GCF? Which one do you have to use the guess and check method? Do you want to replace sine of theta with x? So just think about those things, write down those important things in your summary, and let me know if you have any additional questions in class.